This brings us to autoregression. The first order autoregressive model. If you want to predict the GDP growth rate in the next quarter, a good place to start is last quarter's GDP growth rate. So remember, we're dealing with time series. We know there's some amount of information in today's GDP, for example, or whatever our time series is, that can predict the future GDP or our future time series. So a good place to start for predicting today's GDP is yesterday's GDP. A simple way to do this is to put GDP today in time period t. Let me get my pen out. GDP today in time period t will make that a function of GDP last quarter. This is called the first order autoregressive model. We can use it to predict GDP growth rates, so GR is the growth rate, and t plus 1 in the future. The coefficients suggest that there's a positive growth in one period is associated with positive growth in the next period. We have a coefficient of 0.344. That means that the growth rate, if it's positive in one period, we're likely to have a positive growth rate in the next period. The abbreviation for this is AR1, or autoregressive 1. The population model is written here below. So this looks just like a standard OLS model that we've seen with one regressor, except now we're replacing x with yt minus 1, its previous period value. Okay, so forecasts and forecast errors. We can use the model to make forecasts. That's kind of the benefit of time series analysis. The forecast in period t plus 1, or the next period beyond our data, is written y hat t plus 1 conditional on, remember this line means conditional on, everything that happened in big T leading up to t plus 1. This is equal to beta hat 0 plus beta hat 1 times y capital T, the last time period. This is not the same as the predicted values in a regression because y hat t plus 1 conditional on t does not have a corresponding value in our data. We are predicting out of sample. So what do we mean by this? This means that if we have x and y, what we've been doing so far, we might have some data points, and we fit a line to these data points. And we use our regression, say this is x2, y2, then we use the regression line to predict y hat 2, right? And we had the residuals, u hat 2. But this y hat 2 corresponded to a real data point here, x2, y2. In this case, with time series, we're predicting out of sample. So now we're going to go out to some place out here, xj, where xj doesn't exist in our data set. We're going to predict what our y is going to be, y hat j, outside of our data set. So this is the forecasting part. This is why it's not the same as using or getting predicted values in the regressions we've done. The forecast error. The forecast error is written as the observed value minus the predicted value. So to get the forecast error, we need to wait until yt plus 1 actually happens. It is the realized value in the time period t plus 1 minus the predicted value, not the same as the regression error. We can characterize some kind of uncertainty about this error, and we call this the root mean squared forecast error. It's a measure of the size of the mistake of the forecast error, or the magnitude of the typical mistake. For the population value, it's equal to the expected value of yt plus 1 minus its predicted counterpart squared. So it's essentially the variance with a square root that gives us the standardized variance or the standard deviation of our forecast errors. The root mean squared forecast error has two sources of uncertainty. The first is the uncertainty arising from predicting future values. In other words, the future is unknown. So when we have our model here of yt plus 1, we're predicting based on our first order autoregressive model with yt here. Let's say we're predicting out to yt plus 2, and we're going to use yt plus 1 to predict out to yt plus 2. we don't know what yt plus 1 is, and so we have to use our prediction of yt plus 1 from the previous model of yt to get a prediction of yt plus 1 in order to predict yt plus 2. So we have uncertainty in simply just not knowing what the future is going to be. And then there's uncertainty in the regression equation. Just because we've written down this model this way doesn't mean that we've got the regression equation correct. Remember when we talked about omitted variable bias in the regular multiple regression scenario, we spent a lot of time on getting our functional form right and dealing with omitted variables. We still have to think about that in the time series analysis, because if we're getting these betas wrong, then our regression forecasts are going to be wrong. So an example, an application of GDP forecasts. What is the forecast of GDP growth in the first quarter of 2013 that an economist would have made in the fourth quarter of 2012 based on the AR1 model? So the growth rate of GDP in 2012, quarter 4, was 0.15%. So we can write that as follows. We can plug this value into the GDP growth rate equation that we had on the very first slide. These were the coefficients. Beta had 0, beta had 1, and this is, we had GDPGR in time period t. So we're plugging in 0.15 into this model and getting a predicted value. So just like we did with multiple regression, we're getting predicted values. It's just that this is predicting out of sample. So the math hasn't changed, it's just the interpretation. So the AR1 model forecasts GDP growth rates in 2013 quarter 1 to be 2%. So these two values are equivalent. The forecast error. The actual growth rate, we waited until 2013 quarter 1. We found that the actual growth rate was 1.1%. So the forecast error is 1.1 minus 2 equals negative 0.9%. The adjusted R-squared of the model is only 0.11, so the lag values only explain 11% of the growth rate. Not a lot. There's 89% of the variation that's still left unexplained. The root mean squared forecast error is 3.16, so our estimates of the average forecast error is therefore 3.16 percentage points. Not great. The pth order autoregressive model. So can we do better than just adding a single lag? Yeah, of course we can. The AR1 model uses yt minus 1 to forecast yt, but this ignores potentially useful information in the further distant past. So we define ARP, the pth order autoregressive model. So we can add yt minus 1, yt minus 2, all the way up to yt minus p, where p is any value between p is any value greater than, essentially, I guess in this case, 1, greater than 1. P is greater than 1. So, for example, the AR2 model for GDP. The AR2 model for GDP growth rates is simply adding GDP growth rate in t minus 1 and GDP growth rate in t minus 2. And this gives us the sample output. So our estimates of beta hat 0, beta hat 1, and beta hat 2. Adding GDP growth rate t minus 2 increases the R-squared and decreases the standard error of regression. This will do a better job of forecasting. These models assume OLS assumption 1 holds, in that the expected value of the error term conditional on all the included regressors is equal to 0, which implies no serial correlation in the errors, or the errors are independent. Can we do even better than autoregression? Okay, so what are we looking at here? Let me give you some words about this. So the graph on the previous slide shows interest rates on long-term and short-term bonds. They move together, but the difference between the two is not constant over time. Okay, so we have 3-month, these are short-term bonds, interest rates, and a 10-year, a long-term interest rate. You can see that they move together. The trends are here going up, and then the trends are going down. But there is some difference between the two, and that's what this bottom graph is showing. This bottom graph is showing the difference between these two, and that's called the spread, or the term spread. And so maybe this term spread can help us predict GDP, so long as the term spread is somehow correlated with GDP. So the difference between the long and short term is generally positive but falls to 0 before the recession. So the recession was in 2008. Right here they're talking about. The term spread might contain information about future GDP growth that is not already contained in past GDP values. For instance, the difference between the two measures indicates investors' beliefs about near future relative to the distant future. So it's not so important that you understand why term spread could affect GDP, but what we're getting at is we're building up to adding covariates to the autoregressive model. It's not enough to just say that past values of GDP growth rates are good predictors of the future GDP, right? GDP growth rate in t-2 and t-1. Now we want to add additional control variables. In this case, they've added the first lagged term spread in the AR2 model. That's this last variable over here. The coefficient on term spread 1, term spread t-1 is statistically significant, and the r squared increases from 0.14 to 0.16. That's good. We want to increase our r squared. The forecast using this model is 2.2% with an error of negative 1.1%. So maybe we can even add more lags. So here we have the GDP growth rate in t-1, in t-2, and the term spread in t-1 and t-2. The t-stat on the t-spread t-2 coefficient is 1.53, or a p-value of 0.13. It's not ideal, but it's not terrible. Remember, we want to reject our null hypothesis on a single coefficient, in this case 0.66, that's the one we're considering. We want to reject that null hypothesis with if the t-stat is greater than 1.96, and in this case our t-stat is 1.53. And so maybe the term spread, the two-lag term spread is not a good variable to include in this model. The r squared does go up a little bit to 0.17 from, what did we have before? It went to 0.16 in the previous model. The f-stat on all included spread terms, in other words, we did a joint hypothesis on both of these, the f-stat is 4.43, indicating the model is a significant improvement over the AR2 model, where the AR2 model is just these two growth rates. The standard error of regression goes down slightly from 3.11 to 3.06, but the forecast error actually went up. And so if you're only concerned with forecasting, then you do not want to include the term spread in the model, the second lag of the term spread in the model. The autoregressive distributed lag model. So now we can generalize this. We've just introduced it, but we can generalize it to the autoregressive distributed lag model. In this case, we're adding p lags of our dependent variable, so yt minus 1, yt minus 2, up to yt minus p. And we're adding covariates, and we're adding all the necessary lags of the covariates as well. This should be yt minus q. This should actually have a t on it. It's denoted autoregressive distributed lag, or ADL, of order p and q, where p is the order of the lags of the dependent variable, and q is the order of the lags of the control variables. We must assume that the error is conditional mean 0, which implies all the included lags of y and x are the appropriate number of lags. We shouldn't include more lags, and if we did, the coefficients on those additional lags would be 0.